Hello everyone, Jeff here with a discussion of limits. We are going to first work with the function f of x equals x plus 3, which looks like this. And we are going to try to figure out what this thing here is, which is read the limit of x plus 3 as x approaches 3. And I've also written a description here. What we're asking here is, as we let x get closer and closer to 3, what does x plus 3 get closer and closer to? In other words, let's start by putting in some point like x equals 2. If we did that, we would see that the function takes on the value 2 plus 3 or 5, which we can also see from the graph. When we say let x get closer and closer to 3, we just mean, now let's look at a point closer to 3, like 2.3 maybe. We can see we would get 5.3 out of the function. Moving closer, this is about 2.6, we'd get something like 5.6. Moving closer, 2.9, we'd get something like 5.9. In other words, it looks like as we let x get closer and closer to 3, the function is getting closer and closer to 6. And so we are going to say the limit of x plus 3, as x approaches 3, is 6. Now, we do actually need to check that the same thing is true if we approach x equals 3 from the other side. We would say from the right, and you can see that we would. If we put 4 in here for x, the function will give us 7, 3.5, 6.5, and we're still going to approach 6. So the limit here would be equal to 6. Let's do another example which is similar with something going on here. This is the function f of x equals x squared minus 9 over x minus 3. The difference, although the picture looks very much the same, is that 3 is not in the domain of this function. If we put in x equals 3, you do get 0 in the denominator, which is not allowed, which is represented by the open circle here at x equals 3. But we will still ask the question, what is the limit of this function? What value does the function approach as we let x get closer and closer to 3? Again, we can start with a point like x equals 2. The function does give us 5. I would encourage you to verify that by putting points in. Something like 2.3, you get out 5.3, 2.6, 5.6, 2.9, 5.9, and it does appear that as we let x get closer and closer to 3, this function is getting closer and closer to 6. We would want to verify from the other side as well. We put in 4, we'd get 7, 3.5, 6.5, and again, we're approaching 6 from that direction as well. Note here, the important point, is that we want to know what is happening to the function as we get closer and closer to 3. It doesn't actually matter what the function is at 3. So the limit of this function as x approaches 3 is still 6. We'll change the example slightly here. This is a piecewise defined function equal to x plus 3, the function we've been working with, except that's only when x is not equal to 3. When x is equal to 3, we're defining the function as being equal to 4. So we have the open circle here at x equals 3 because the function is defined as being equal to 4 at that point instead. We can ask what the limit is of this function as x approaches 3. Same argument as before. Something like 2 gets us something like 5, 2.3, 5.3, 2.6, 5.6. Again, we're using the top part here because that's the part that's defined for any value of x not equal to 3. 2.9 not equal to 3, we get 5.9. As we let x approach 3, we are still approaching 6. And again, we'd want to verify from the right. From 4, we'd get 7, 3.5, 6.5, and so on. We are approaching 6. It doesn't matter, again, what the function actually is at 3. A limit is asking what is happening to the function as we approach x equals 3. Get really, really close to it. We are approaching 6 still. Here is another similar but different example. Piecewise defined, we're letting f of x equal x plus 3 for any value of x strictly less than 3, which is why we have the open circle at 3. If x is equal to 3 or greater than 3, the function is now 7 minus x, which is this piece here. If we were to put 3 in here, we'd get 4, which is why we have 3, 4 here on the graph, and so on. We'll ask what the limit of this function is as we let x get closer and closer to 3. Well, from the left, starting at 2, we still have the same thing as before. Anytime we are to the left of 3, we're using the top piece of the function, we're just adding 3. 2 gives us 5, 2.3, 5.3, 2.6, 5.6, and something like 2.9, 5.9. We are approaching 6. Here's the difference. When we look to the right, so we would say approach x equals 3 from the right. Sorry, that's showing as we go from to 3, we get to 6. If we start at a point like 4, we are going to get 3 here. If we move closer to 3 from the right-hand side, we put in 3.5, we get something like 3.5. 7 minus 3.5 is 3.5. If we put in something like 3.1, 7 minus 3.1 is 3.9. When we approach from the right, it looks like we are approaching 4. So here we are approaching x equals 3 from the right-hand side. The function is approaching 4. There's a difference here. What we are going to say, we're going to add a small piece of notation right here, which is to say that the limit of this function as we approach 3 from the left-hand side, that's what the negative exponent-looking thing here is. It's not an exponent, it is just notation. As x approaches 3 from the left, the function is approaching 6, but as x approaches 3 from the right-hand side, which is what this plus sign indicates, the function is approaching 4. When we get different answers from the left and from the right, we are going to say that the limit does not exist. So we're allowed to say that the limit is 6 as we approach from the left. The limit is 4 as we approach from the right. But since we get different answers depending on which way we're coming from, we're going to say that the plain old limit, the limit as x approaches 3, does not exist.